Hello there. In this video we're going to do an application of integration that is going to be focused on finding the length of particular curves. So what is it exactly that we're going to be doing? So let us assume we have some curve in space, and let us assume we have a particular interval of interest, say x is equal to a, 2x is equal to b, and we want to find the length of this curve. So what is the length of that path? So how can we go about this? So what we can do is we can, of course, chop this up into little pieces and approximate the length of this curve. And how are we going to do that? Well, one possible way is we can just use one interval and use a right triangle and use that hypotenuse length as the approximation to that curve. Or we can zoom in to this curve and we can look at a bunch of right triangles and find the hypotenuse length of all of them. And if you do that infinitely many times, then the sum of all of the lengths of the hypotenuses should approach the length of the curve. So for each of those, so for each triangle, let the length be delta x and the height be delta y. So that is for each of these little triangles, we have delta x and delta y. And this is, I guess you could call it RK for each of these ones. So this is like R1, R2, R3, R4, you know, a squared plus b squared equals r squared type of things. And we're going to add up all those r's. Alright, so the length approximation. So how can we find RK in this equation? So we know RK squared is going to be equal to the square root of delta x squared plus delta y squared. So we're going to sum up all of those RK squareds. So this is going to be approximately equal to the sum from k is equal to 1 to m of the square root of delta x squared plus delta y squared. So how can we make this more exact? Well, we can increase the number of partitions that we have. So if that is the case, that means L is exactly equal to the limit, as n goes to infinity, of the sum from k is equal to 1 to m of the square root of delta x squared plus delta y squared. But exactly what is this that we're looking at? So we can rewrite this expression. So we can rewrite this as the limit, as n goes to infinity, of the summation from k is equal to 1 to m, and we can factor out delta x squared out of this expression. So what would that look like? So if I factor out delta x squared, that's going to be 1 plus delta y squared divided by delta x squared. And then I can take the square root of this delta x squared, that's just going to give me delta x. So this is just going to be equal to the limit, as n goes to infinity, of the sum from k is equal to 1 to n of the square root of 1 plus delta y divided by delta x squared times delta x on the outside. And what exactly is this? Well, that is just a definite integral, actually. So that means L must be equal to the limit, the integral from a to b, of the square root of 1 plus, so once we take the limit, delta y approaches dy and delta x approaches dx. So it's going to be dy divided by dx, the quantity squared, dx. And this is the formula for arc length, where y is equal to f of x, the function of interest. So let's work through an example of how to calculate this. Alright, so example, so let y be equal to the hyperbolic cosine curve, and let's calculate the arc length on the interval 1 to 3. So if y is equal to the hyperbolic cosine, then dy dx is going to be equal to the derivative of hyperbolic cosine is just going to be a hyperbolic sine of x. So that means dy dx squared is going to be the hyperbolic sine of x squared. So therefore, the arc length, which I'm going to call L, is going to be equal to the integral on the interval of interest, 1 to 3, of the square root of 1 plus dy dx, the quantity squared. So that's going to be sine h squared of x dx. So recall that hyperbolic cosine squared minus hyperbolic sine squared x is equal to 1. So that means 1 plus hyperbolic sine squared x is just going to be equal to hyperbolic cosine squared of x. So that means the arc length, why did my integral go that way? That was written correctly, just sloppily. So this is just going to be equal to the integral from 1 to 3 of the square root of hyperbolic cosine squared of x dx, which is just going to be equal to the integral from 1 to 3 of hyperbolic cosine of x. So the antiderivative of hyperbolic cosine is hyperbolic sine. So this is going to be equal to hyperbolic sine of x, evaluated as x goes to 3 and as x goes to 1. So therefore, the arc length is going to be equal to hyperbolic sine of 3 minus hyperbolic sine of 1. And that's the exact answer, and you can use approximations to hyperbolic sine if you desire. Now, that's how you find the arc length of functions, but there is something that one really needs to keep in mind. So we have the integral from a to b of the square root of 1 plus dy dx squared dx. So notice that this function is under a square root. We've done several videos so far on, say, trig substitution or substitution, where those may give you strategies on solving these integrals. But there are several basic functions that you may want to find the arc length of. For example, suppose we want to use like the square. So y is equal to x squared on 0 to 3. So let's assume we want to find that arc length. So that means the arc length would just be equal to the integral from 0 to 3 of 1 plus, well, the derivative of y with respect to x is just going to be equal to 2x. So once we square that, it's just going to give us 4x squared dx. And actually, even trig substitutions won't be able to evaluate this. So how can we find that value? So what we can do is approximate it with rectangles or trapezoids. If we want, like we did in the original approach to definite integrals. But in terms of finding the exact solution, that's not always easy. Actually, there is no elementary antiderivative for this function. We haven't talked about what it means to have an elementary antiderivative, but we will eventually. But this is one of those examples where you actually cannot find the antiderivative of it. So just keep that in mind. You know, if you keep on playing around with some of these integrals, it's possible that there is no antiderivative that exists. But we'll get there eventually, but just keep these things in mind when you're working with some of these basic looking examples, because they're actually not that basic.